Hi, welcome to this video about the influence of particle concentration on settling. And the idea for this video is that we learn what happens if we have more than one single particle which settles. I will comment this on the next slide. And then we take a look at different models or model approaches to describe this problem of multiple particle settling. And finally, you learn about the Richard-Zaki or Richardson-Zaki equation, which we mainly use to describe the particle swarm settling. So yeah, that's the idea for this video. And so if you think about what we did in the previous videos, and there's a bunch of videos where we repeatedly looked at the problem of the movement, mainly settling, of a single particle. So we look at one particle, and this one particle moves, mainly it settles down, and we try to describe the settling by, for example, calculating the settling velocity, settling time, or a crucial size of the particle, and relate this to different unit operation. However, the assumption behind this model or the approach is that these single particles we calculate or look at don't influence each other if we have more than one. And if you think about most unit operations as, for example, sedimentation or fluidization, which we don't discuss so far, but basically is the movement of a lot of particles in a reactor, then this is not the case. We don't have a single particle, and this means our approach is, for calculating with one particle, is maybe a little bit questionable or not perfect. So what we want to do is that we say, okay, what happens now if we have more than one particle, if we have many? And in the case, or in the models we're considering, or the case we are looking, we neglect one very important thing, and this is adhesion. So we say there's only a weak adhesion between particles in my system, and this means we don't have coagulation or flocation. So the particles don't form strong clusters. But what we have to consider is that particles, if they move down, they carry fluid around them. So fluid is somehow sticking to them, and if the particle moves down, the fluid sticks to the particle, also moves down, and at the same time, if the particle moves down, it pushes also fluid to the sides. And based on this, so the particle goes down, it carries fluid with it, it pushes fluid to the side, we would create low pressure area above the particle. And since we have continuity, this means there is a counterflow upwards. This means because the particles, they settle down, they carry fluid with them, fluid is pushed to the side, and this means we need a counterflow to keep continuity, which goes upwards. And if we now have an upwards counterflow, which we don't consider it for a single particle, this means we have now a reduced settling velocity, and this reduction increases with increasing particle concentration. So if we don't look at an individual single particle, but at multiple particles which settle down, it means they settle slower, and they settle the more slow, the higher the concentration. Okay, and this is basically what we have to consider and what we don't consider if we look at only one single particle. So I take this picture, which you maybe know from previous videos. So this is a sedimentation tank or a thickening tank, and we talked about this when we talk about precipitation and sedimentation of lithium carbonate for lithium-ion battery production, where we need lithium or lithium carbonate as a resource to get the battery materials. And here we have lithium carbonate, which is in form of small particles in water. And so far we said, okay, here is a lithium particle, and here's a lithium particle, and here's a lithium particle, and the lithium particles slowly settle down, and by this we get a higher concentration on the bottom in the tank than in the top of the tank. However, this is a very, very simplified picture, right? Because normally we not only have a particle here, and a particle here, but we also have a particle here, right, next to it. And we have one here, and we have one here, and here, and here, and everywhere we have these particles. And this is exactly the problem. We have so many particles that we have to consider the amount of them when take a look at the settling time in this thickening tank. And the movement of particle collectives generally is influenced by momentum exchange. And momentum exchange means the exchange between particles or between the fluid and the particle. So if we want to describe now the movement of not a single but of a collective, of a swarm of particles, we have to consider momentum exchange. We have a changing hydrostatic pressure which affects this movement. We have turbulence within the flow, right? The flow can move, so the water where the lithium particles are in can move. And we also have attractive or repulsive forces. So there are a lot of things which can influence the movement of these particle collectives. And what is important to realize is that till today, we only have very, very simple models for these very complex systems, right? Complex systems because we have all these points which we have to consider, and the models we have today are much too simple to describe all of this. But we can also make some statements, and this is that if we neglect coagulation, flocculation, so we don't have attractive or repulsive forces, this is out for the models. Things are a little bit simpler. And if we don't have any turbulence within the flow, so the flow basically, the liquid where the particles are in is basically not moving by itself. There are movements because of the settling of the particle, but generally the liquid is silent, it is not moving. And then we can say if we have an average particle distance, so we have a particle, another particle, and the average distance between them, which is A, the distance between the particles, and this is larger than 6 times the diameter. Then we have a concentration of particles in the liquid, or in the fluid basically, which is below 0.25%. And in this case, we can take our own old approaches of single particles. So if we have a very, very low concentration, lower than 0.25%, we can consider particles as individual particles and calculate with the simple force balance. And then we have something very interesting, which is normally in the models we have so far, because we only have very simple models, not really considered, is that in roughly between 1% and 5%, the settling velocity of the particles can even increase compared to single settling velocity. So in this case, in this concentrations, the collectives can settle faster, not slower. And this is because in this region, particles form cluster. And they don't cluster because of attractive or repulsive forces. They cluster because they randomly move. And there are areas where some more particles, and there are areas where no particles, just by chance. And the areas with more particles, they form a small cluster, and this leads to a faster movement. And these clusters are highly dynamic because the particles don't stick to each other. And this is also normally not considered in our very simple models. And then we have another point, and this is that so a fluid is a gas or a liquid, but generally if we look at gases, the loading of particles is very limited. So this means we can neglect the influence of collectives. So in gases, we consider individual particles as individual particles because the loading is not that high. But in liquids, the loading of particles can be very high. And then we have to look at particle collectives when we want to understand better the settling of particles. Okay, so there are different models which we can use to describe the sedimentation. And here I want to give you first a very general overview, and to describe the particle swarm sedimentation, a large amount of models can be grouped, and now it's important, into empirical, semi-theoretical and theoretical models. The last The two last are based on hydrodynamic principle, which can be grouped into, and I will show you this in a minute. But what is important, empirical means you measure how fast particles settle, you increase the concentration, measure again, increase the concentration, measure again, and then you plot the settling over concentration. Then you take Excel or any kind of tool you would like to take. You have your data points, and then you ask Excel, can you make a graph through it? And then you get a very nice line, and this is a complete empirical model, because you don't have any understanding of the line, you just have data points, and the line somehow reflects your data points without any theory behind. And then you can have and this is an empirical model. And then you can have a semi-theoretical model. And this is when you take now your line and you think a little bit about it and say, the line shows a quadratic behavior, and the quadratic behavior somehow shows me a physical principle. And this physical principle is very nice described by this quadratic behavior. And then you already have some theory behind. Or if you, for example, put some constants or whatever based on theory in it. And then you have theoretical models, and theoretical models are the force balances we made for the individual particles, right? So you make a model, and the model is completely built up from theory, not from what you measure. And for the two last, they are mainly based on hydrodynamic principles, and they are grouped first and then you take a suspension as a continuum where its density and viscosity is determined by the particle properties and concentration. So what does it mean? It means you have particles in a liquid, and you don't consider them as different phases. You say, okay, this suspension of particle in liquid is one continuum. And the density and viscosity of this continuum is determined as well as by the liquid properties as the particle properties and the concentration of the particles. So you describe this suspension with one viscosity and one density. And then you just calculate swarm settling velocities in the regular way. So regular way means individual particle with these adjusted properties. So this is one way of, or one group of models we have. Then solids are considered as a flow through particle bed. And these are the so-called flow equations. And the flow equations, we will have an additional video about flow equation. And this means you have a bed of particles and the fluid flows through this bed. And flow equation describe how the fluid flows, what is the pressure drop, and so on. And you can also use this as an approach to describe the swarm sedimentation of particles. And then the mainly used type of models is that the suspension is a two-phased system considering the properties of each single phase. So this means you have two phases, the liquid and the particle, and you consider the properties of the particle and the property of the liquid separated. And this is basically the typical models we use to describe these swarm sedimentation. And here you see an overview about different of these models. So what you see here is the swarm settling velocity divided by the individual settling velocity. So if you think about the lithium, so we take the model and we calculate the swarm settling velocity of the lithium particles, and we calculate it for one single lithium particles, as we did it in the past, and then we make the ratio. And since the individual settling velocity is larger than the swarm settling velocity, the value is between 0 and 1. 1 is if the swarm settling velocity is the same as the individual settling velocity. And this we plot over particle concentration, because with increasing particle concentration, the swarm settling velocity decreases, and this means the ratio also decreases. And here you see different models, for example, Richardson-Zaki or Richard-Zaki, Steiner or Barnea and Mizrahi. And you also see that the Richardson-Zaki is in Stokes and Newton regime, and there is quite a large difference, which makes sense, right? And also Steiner, where you have the experimental and polynomial form, which are also very, very differently And these models are somehow semi-empirical. And you see that if you look at the concentration between at 10%, that these models can give to very, very different results, as we have here Richardson-Zaki and Newton regime. And here we have the Steiner. So we have values between 0.75 as the ratio and 0.5. So this is a big difference, and therefore these models can really show or lead to different results. And based on this, the main model which is used to calculate these particle the swarm settling velocity, is the Richard-Zaki. I don't want to go in all the details of the models, just important that you know they are different models, they are very different in their results, and the main model is this one, and this is what you see here, the so-called Richard-Zaki equation or Richardson-Zaki equation, and this is the most important mainly used model, and this generally works to concentrations of 0.3, but if you make the math, you can calculate whatever you want. Here I calculate with 0.5, but generally this model works to 30%, 0.3, and it works for both sedimentation and fluidization. And the model is very simple. So here is the swarm settling velocity. This is what we normally want to calculate. And here we have the terminal settling velocity, and this is something we normally calculate based on the theory you already know. And then we have 1 minus CV. This is the concentration, so you need to measure or know the concentration of your suspension. And then we have an exponent, and this exponent is alpha, and alpha can be between 2.4 to 4.65 and depends on the Reynolds number. And here you see how. So for low Reynolds number below 1, it's 4.65, and then it gradually decreases till a Reynolds number of 500, and then it's 2.4. So with increasing Reynolds numbers, this exponent changes, and you have to be careful because with increasing Reynolds number, also the model you use to describe the terminal velocity changes, right? And this is why you saw in the previous slide the Richard-Zaki equation for Newton and for Stokes, because Stokes has a different individual sedimentation velocity than Newton and a different exponent. But generally, it's a very, very simple model which very well describes the swarm settling velocity. Okay, I have some tasks for you to train your knowledge, because I talked a lot about models and swarm settling velocity, and I want that you understand what I'm trying to explain here. So, first of all, at one of the slides, we had the statement that the average particle distance, or when the average particle distance A is larger than 6 dp, so the diameter of the particle, the volume fraction is below 0.25%. Show that, calculate that. It's a very nice task, very simple, but calculate this. Just don't take the statement as greater, try to calculate why this is the case. Then we have a suspension containing spherical sand particles of a diameter of 100 micron. The water has a temperature of 20 degrees Celsius, and the solid volume fraction is 0.12, and this is not in percent, so it's 12%. And the density of the particles is 2,650 kilogram per cubic meter. Density and viscosity of the water are 998 kilogram per square meter. So we are very precise here for for cubic meter. And the viscosity is 1.002 10 to the power minus 3 Pascal seconds. And with this, I want you to calculate the swarm settling velocity of these particles based on what you learned in the video. And then the last question is, what changes if the particle size is not 100 micrometer but 250 micrometers? So I think these are very easy but nice tasks that you can repeat and train your knowledge from this video. And with this, I would like to sum up. So I hope that you learned what happens if we have more than one single individual particle which settles, and I try to give you insight in different model approaches very generally, and then show you some models which are used. And finally, you learned about the Richard-Zaki equation, which is mainly used to describe the particle swarm settling. And with this, I would like to thank you for watching the videos, and if you have any questions, feel free to ask me.